Welcome back to the second chapter of Big Data for Engineers. This is mostly going to be a SQL brush up. So I'm going to start with a word of warning. One or two things is going to happen in the next hour. Possibility one, you're going to be bored because you've already seen that already. You've been in information systems for engineers. That's just a brush up. So it's just an opportunity to make sure that you're up to date. So you're going to be bored. The other thing that's going to happen is that you're going to be scared because I'm going to dump at you one semester's worth of material on SQL, and don't worry about that because you don't actually need to catch up in 1 hour the whole course. The only thing that I really want you to do, the whole point of that, is to learn SQL. And in fact, SQL is a very easy language to learn. Right? And you'll have a notebook next week with exercises on SQL. What is SQL? It's a query language to manipulate tables. So do not be scared, do not be bored, I hope. It's a good opportunity for a brush up. I'm just saying that to you so that you don't worry. This is really a special lecture. This is just a brush up. And next week, we will start with the actual contents of this lecture. And the reason why we brush up on SQL, there are several reasons, but SQL is going to come back in this lecture later because we're going to use SQL again on top of Apache Spark and at other places, right? So this is why you actually have to know SQL. A lot of people use libraries in Python, to manipulate tables, but it's worth learning SQL because you will see you can use it in a notebook. It's super easy. You can write the SQL query in a few lines in a cell and click on execute. Then you get an output table. It's really, really super easy. All right. So again, I repeat, the one assignment that you will have next week is to make sure that you learn the basics of SQL and that you follow the exercises. Right. Do not be bored. Do not be scared. All right. With that said, I'm going to ask you a question on your knowledge. SQL, it should be yes, this one. I just want to get a feeling of how many of you will be bored and how many of you will be scared, basically. So tell me how familiar you are with relational databases. I saw a question, by the way, on Zoom. There cannot be any preponements, right? You really have to come on exam day. Well, we have power users of SQL. Okay, so it's distributing evenly. Some people never heard about it, 1/3 roughly. Some people 1/5 know the basics, but you need to brush up. That's also okay. And some people already know quite well the model, the algebra, the SQL query, maybe from the information systems for engineers. Wherever you are, you don't need to worry, because this is why the information systems for engineers, it can be taken later. You can take it, in the movies, it's called a prequel, right? You have a movie and then a later movie actually happens before the first one, but it still makes sense. So it's the same here. You really don't have to worry if you don't know yet the details. All right, now let's move on and do the brush up with that word of warning. I'm saying that because I want you to come back next week, right? So I just want you that you're aware that this is really special and this is just a brush up and the actual material will start next week. All right, so now I'm going to switch back to the slides. There you go. Okay, so this is Edgar Code. I don't know if you've seen him before. He's the one who wrote history with databases and came up with this idea that relational tables are so simple that this is the only thing that people should ever see when they interact with a database, right? What does it mean? Data independence means that there is a level of abstraction. This is what the user, you, see, right? A table, a relational table. And then there's the implementation. This is what's hidden from you, what you don't see, because this is what the computer is taking care of. So this is what you see. This is actually what you literally see in the Jupyter notebook. You will actually see tables like this displayed on your screen. This is what you do not see when you use a relational system. Because of course, all of that is stored in files on the hard drive. But good news, you don't need to know about them and you don't need to even know the details of that. This is hidden. This is all hidden here. You don't even need to know about that. So this is the physical layer. This is the logical layer, right? And data independence means that you can change what's there. You could actually implement a relational table on a clay tablet. This is how people did it thousands of years ago. It might be a bit slower. I wouldn't expect an answer in 2 milliseconds as today, but it works. It is also a perfectly fine physical implementation of a relational database management system. A spreadsheet, you could argue, is kind of an implementation also of a table, but you have to be very careful because if you mess it up by offsetting a row or a column and you are in charge of a publicly visible organization, you're going to be in the news. That actually happened a few years ago in Great Britain. So be very careful if you use spreadsheets because this is easy to make mistakes and get the data wrong. You can also do it with PostgreSQL. In our case, we're going to have PostgreSQL, which is a software that basically handles relational tables on your laptop. In fact, on Docker, which is on your laptop, you're going to run a mini version of that. But in this lecture, we will also swap the disk for a cluster of machines. We will also be using relational tables and SQL on plenty of machines, right? And you can do it on DNA. I told you some people did it on DNA. Do you see the magic here? That doesn't change. This is just a relational table, and we can swap here what we implement it on. The user doesn't care. It remains a table. This is the good news. This is the power of data independence. The user doesn't need to know about what's happening on the physical layer. They are just manipulating a table. Tables, thousands of years old. Everybody understands tables. All right. A reminder that there are 5 fundamental shapes of data. If I repeat it, I'm sure you will remember it. Tables, trees, unstructured, cubes, graphs. These are the 5. And in this lecture, we'll focus on tables and on trees, mostly. But today, for the brush up, we will start with tables because these are the ones that we started with in the table, in the database world. So what do we have? When we have, it's called the technology stack. That's how computer scientists call it. We need a way to store things. So the data has to be physically stored somewhere. It's always going to end up on some hard drives or DNA or crystals or whatever, but you need to store it somewhere. This is a hard drive. Then there is a level of computing. This is typically the CPU for central processing unit, right? This is the brain of the computer. This is what it looks like if you've never seen one. And then we go higher in abstraction. There is a data model, which is the relational model. This is basically how you model the tables, just like a model in physics, but it's a data model. And then there is a language, in that case, SQL for the perspective of the brush up. Of course, it exists if you have a different model, then you have a different language, right? But this is basically the overall architecture. Now, what is a model? This is something that tells you what data looks like and what you can do with it, right? You can compare it with cooking, right? A model for cooking basically tells you what food looks like, something that can be eaten, and maybe you can classify it in plenty of categories. And then what you can do with it, you can mix, pour, break, dry, bake, grill, melt, mince, mix, like all the things you find in recipe books, right? So this is an example for a model of cooking. We just do the same with data, right? Something that I also want to show you is that because of data independence, we can keep the model and the language that are here and swap the physical level, meaning that we will start with the Docker, we'll have a single machine with a single hard drive and a single CPU, and we'll go all the way to clusters of machines. But again, data in the, wait for it, pendants, it's all over there. Doesn't care if you have a single machine or if you have a cluster of machines. All right? So what is a data model for relational tables? I'm going to try to keep it simple and high level, but you will see this should be relatively easy. What do you have to know about the tables? First, that it's called a table. But you might also hear, especially in the context of big data, the word collection, right? You can view a table as a collection of rows. right? It's a perfectly natural way of putting things, right? So you might hear table, you might hear collection. So a table is this. So it's a collection of rows. What is a row? It's this horizontal slice right there, right? This is a row. It can also be called a record. It's a database record. So if you have a list of people, then you have one person on every row, can be called a record. It can also be called a tuple. That's just synonyms, right? An entity, an item. Oh, a business object. I love that one. This is how the business people call it. A business object. This is what they call the a row in a relational table. But these are all synonyms. You can use whichever you want, right? They all mean a row. Okay. So a row is something that you describe in your system, and a table is just a collection of some things, collection of rows. Then we have the columns. So you've already seen a spreadsheet, right? What is a column? For example, it's the first name, or there is a column for the birth date, and so on and so on, right? So these are all the attributes. And again, you have the synonyms. You can say column, you can say attribute, you can say field, you can say property, you can say key. There are so many ways that you can call them, but again, these are all synonyms, right? So this is a table that you can see as a collection of rows, but you can also view them as columns, right? And every row has information for every column, right? Who is following? Should be simple enough, right? It's very, very abstract. Now, very often, there is a column, several columns that are special. If you have a list of persons in Switzerland, let's say you're the tax office, and you have the list of all the taxpayers, what do you think a column that identifies a person is going to be? How does the government identify a person in Switzerland? Yes? Yes, so the social security number, basically, yes, exactly. So that's called AHFA or AVS in French, right? So indeed, there is this social security number that everybody in Switzerland who worked is getting. And for example, the tax office is using that number to identify you. Well, there is a column in that table that could have this social security number. And this is called the primary key. What does it mean? It means that this is enough to know who you are, right? The first name alone is surely not a primary key. If I tell you it's Peter, then you don't know who is Peter. There's plenty of Peters, right? But with social security, then you know exactly who that person is. This is called the primary key. Can be one, can be multiple columns, but this is basically one of the columns or several of the columns that are special. Okay, that's pretty much it about tables. You have tables that are made of rows and columns, and some columns can be a primary key. That's really it. That's what the relational model is about. Then you can formalize this a little bit more, but again, I'm not going to do it in the same level of details as in the lecture, but I just wanted to make you realize, because you might be wondering, why do we call that a relational database? Why is it called a relational database management system? Well, it's just because mathematically a table can be seen as a mathematical relation, and this is why it's called relational. Who is a mathematician in here? You have some mathematicians. So you know what a relation is, right? It's basically a subset of the Cartesian product of the domains on which you define it, typically with two, but in databases, we do it with more than two domains, right? So D1, D2, D3, and that's a subset of the Cartesian product. So you can see basically, this is why it's called tuple. It actually comes from the vocabulary of relation that not near enough. This is a tuple, this is a tuple, this is a tuple, this is a tuple. And a tuple is really just a list of values taken. This comes from the first domain, this comes from the second domain, this comes from the third domain. For example, this could be a string for the first name, a string for the last name, and here a birth date, that would be a date, right? And then you have first name, last name, date. So you can either view it as a table like this or as a mathematical relation. If that doesn't make sense, you don't need to worry about it. I'm just saying it, out of curiosity, but you really don't need to understand that to follow the lecture. This is just to let you know why it's called relational, and that's because of that. Okay, so technically, how can we formally define what a relational table is? I'm not going to use the relational definition. It's in many textbooks, but I think it's a bit imprecise. for many reasons. One of them is that when you have a relation, there is an order in the values, but in a relational table, there is no order in the columns. If you swap the columns, it's still the same table. That's one of the reasons why it's not entirely satisfactory. But actually, there's an easier way. How do you define a relation or a table? Doesn't matter how, if you call it a relation or a table, I use them interchangeably. First, you have a set of attributes. What are the attributes? It's the headers. It's what you have on the first row in your spreadsheet, right? So that's last name, first name, country, and so on. Set of attributes. And then you have what's called an extension, which is just a fancy name for that part right there, right? It's basically a set of tuples, right? So basically, this is one tuple. What does a tuple do? It associates, let's look at this tuple. It associates last with Einstein, first with Albert, and country with CH, right? You can also draw it that way. I even added a year here that wasn't on the previous slide. This is basically some sort of mapping. It's technically called the partial function that associates every one of the attributes that you have in your headers with some value. Last Einstein, first Albert, country CH, year 1905. What are these fancy letters? This is just a way, it's not official, right? But this is just to say this comes from the set of strings. So a string is just a bunch of text in computer science, and V is the set of values. Again, this is not official. This is nothing that is conventional. So technically, a tuple maps some of the attributes to values, right? You can see it as a partial function. If you're a mathematician, if you're a computer scientist, you would call it a map. But basically, this is what it is. This here is one row. This is this, except the year that I said the year doesn't appear here. But this here can be seen as a tuple like that. For whom is that clear? Okay. But of course, I don't think many data scientists view it like this. Many data scientists would view it like this. This is how they visualize it, right? This is much more natural to see that it's equivalent. It's twice the same thing. But this is more natural to do, right? This is one row together with the headers, but this is one row of the table. The order is totally irrelevant of the attributes. It's not part of the model. So if I had name and then physicist and then first name and then year, still the same tuple. Okay, so this is a tuple. And again, it's also called a row, a record, a business object. If you want to sound fancy, this is basically what it is. It's a map from attributes to values. Okay, now how about several tuples? Because we need a table. This is not, well, this is a table with one row, but in reality, we have tables with billions of rows, right? So how do we do that? Well, we take plenty of tuples, right? So here I have 3 tuples that I represented each with their headers. But of course, this is also not how you draw a relational table, because as you might have noticed, all of these tuples have exactly the same attributes. So what do? Well, you compress it like that, right? This is what you have in a spreadsheet, right? But this is only possible because they have the same attributes, right? And we see in big data, they might not have the same attributes, as we will see. But in relational tables, as we saw in information systems for engineers, they have the same attributes, and we can display it in that way. This here is a relational table. You might have noticed that I said here it's a set of tuples. So here, this is a set. It means that there are no duplicates and that the order is irrelevant. If you change the order of the rows, it's still the same table, right? Because it's considered to be a set of tuples. Either a tuple is in the table or it's not in the table, but you don't have a notion of cardinality and you don't have a notion of order. But some people like to extend the model here as bags and lists of tuples, which is also possible, but the standard relational model has sets of tuples. Okay, now I'm going to break things, because actually in big data for engineers, we're going to break these things. So I'm really sorry, I apologize in advance for those of you who were used to the beautiful world of information systems for engineers where everything was a nice table. Now we're going to break things. How do we break what's called relational integrity? Relational integrity is just for saying that the tuples have the same attributes. This is an example where it's broken. How do I see it's broken? Well, this tuple right here has an extra column called country that the others don't have. There is a missing value for name here. You see, it doesn't plug into the table. And here there is a missing value also for physicists. So you see, this fits relational integrity. This breaks relational integrity. This here is not a relational table. This is a relational table. This is not a relational table. This is one of three. Let's break something else. Let's break something called atomic integrity. Atomic integrity means that all of the values that are in the cells, they are atomic. It can be a number, it can be a bit of text and so on, but it's much easier if I show you a counterexample. This is a counterexample. This is a table in a table in a table in a table. It's like the Inception movie. I like to compare it with the Inception movie. Who saw Inception? It's a dream in a dream in a dream in a dream. It's the same thing here, a table in a table in a table in a table. In relational tables, normally you don't allow that. This is forbidden. This is forbidden, and this is said that it's said to be breaking atomic integrity. This is okay, this is not okay. That's the second rule. And of course, we're going to break it. In big data, we're going to accept that. This is new. In fact, this is how we get trees, but this is another story for in a couple of weeks. Okay, let's break something else. The third rule that we're going to break is called domain integrity. You might have noticed in this table that there is some regular pattern here. You might notice, for example, that in the last column on the right, you only have integers. These are years. On the third column, you have Booleans, true, false. This is called domain integrity, where in every column, you have a specific domain and specific types. So again, a counterexample is great to show you how we can break that. This is broken. You see the second tuple has 0 in there. 0 is not a Boolean. It can be interpreted. In some programming languages, you can still interpret that as false, but it's not a Boolean. This is breaking this rule right here. And this here is text 42. Of course, if you're a human, you can still fix it, but that would be an unclean data set. This is not an integer. You would have to actually write it as 42 or 1942. Right? Okay, so this is breaking the domain integrity. And this is when we have the domain integrity. So you see, you can break three things. You can break the relational integrity like this. You can break the atomic integrity like that. And you can break the domain integrity like this. So there's three ways that you can create a big mess. This is messy data. And if you are in the intersection of the three rules, meaning that you're breaking none of the three, you are in the beautiful world of relational databases. And you can use SQL to query the data. But if you break the rules, then you are in the NoSQL, meaning not only SQL realm. And this is what we'll cover in this lecture. So in this lecture, we'll be happily breaking these rules. We'll be looking at tables in quotes where the tuples don't even have the same attributes. We're going to be looking at tables in tables in tables in tables, and we are going to be looking at tuples that might not even have the same types every time for the same column. All right, so this is what we're going to do. But right now, because it's the brush up of SQL, I'm going to focus here on this not breaking any rules. So today, I'm not breaking any rules. Next week, and during the rest of the semester, we're going to break the rules. But here, we're going to stay within the intersection of these three and just manipulate tables, right? Just that. Okay, so the next step, once you have defined these three rules and you consider relational tables, is how do you manipulate these tables? Well, it turns out that just like in mathematics, you can manipulate numbers. So you have the notion of groups and rings and fields and vector spaces and all kinds of structures and fancy structures with operations to manipulate mathematical objects. Well, a table is a mathematical object too, right? So you can also define an algebra. I don't think it's meant as an algebra in the same sense of you mean a mathematical algebra, which is something very specific, but we still call it a relational algebra. And it just means that we define some operators that transform tables into tables or take two tables and return one table and so on, right? So this is called the algebra. What can we do? We can compute the union of two tables, the intersection of two tables. We can select, meaning that we take a subset of the rows. We can take a subset of the columns. That's called the projection. We can rename the columns, change the names of the columns or even of the table. And we can join tables. I will have animations for that. All right, but let's take them one by one, just to give you this feeling or to brush up if you already knew. This is the menu, and now I'm going to show you slide by slide some of them. What's coming? First, a selection basically takes a table, you keep the same attributes, you keep the same columns, but you pick some, but not necessarily all of the tuples. This is typically done with a predicate, and you test the predicate on every tuple, and you keep the tuple if and only if the predicate is fulfilled. For example, here you could say, I want to only keep these tuples or records, or let's call it business objects. So I just want to keep the 2 business objects where B is at most 2. So the business objects foo 3 false and foo bar 4 true, they just go away, right? This is called a selection. Then we have projections. Projection means we keep all the rows, but we only pick some of the attributes. So in that case, we just make B go away. Note that you can do this in Excel or OpenOffice or whatever spreadsheet software you want, right? This also works quite well with the spreadsheet software. Here, that would correspond to hiding a column, right? Control-0, I think, is the shortcut to do that in Excel. Anyway, this is a projection, right? Who is clear on selection projection, what this does? That should be intuitive enough, right? Okay, what is grouping? Grouping is when you aggregate. Imagine, for example, that we have some, let's take the statistical office of Switzerland. They have the population of every Gemeinde, every town in Switzerland, and you want to compute the total population of each one of the 26 cantons. And you have a table with the canton on the left and a count for one of the villages on the right. We drop the name of the village. We just keep the canton and the counts. Well, you can do what's called grouping. So I didn't put cantons in there. I put just fancy things like foo bar. That comes actually, if you don't know, from Furchtbar. And then the computer scientists made a pun with that and turned it into foo bar. So whenever you come up with an example, you use foo and bar and foo bar. But anyway, that's just a computer science thing. But imagine that this is Zurich, Zurich, Zurich. And these are 3 towns in the canton of Zurich. You want to do this, plus which gives you that. Then let's do the same here with bar, could be Schwyz, I don't know, Schwyz, 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 Schwyz. This plus this plus this plus this gives you this, and so on and so on. So this is called an aggregation. You group together and aggregate the numbers, and you might have had the list of all the towns of Switzerland on the left with the canton they belong to and a count, and on the right you have the aggregated view with 1 record per canton and then the population. This is called grouping or aggregating. Then you can sort, but of course, the mathematicians might object. If it's a set, you cannot sort anything. There's no order in a set. But actually, it's fine because some people consider that we don't look at it as a set, but as a list. So you just claim that now the order actually matters of the rows. If the order matters, then you can sort things. And this is also something you can do in a spreadsheet. You can sort alphabetically by first name. You can sort by security number. You can sort the towns of Switzerland by increasing population, for example. This is called sorting. You just, again, need to be careful to use a list semantics and not a set semantics because you want the order to be important. Okay, so you can sort things. Something else you can do is a Cartesian product. If you take 2 tables on the left, you're going to compute all of the possible combinations. All of the combinations with 1 business object from the top table and 1 business object from the bottom table. So if you consider all the combinations, I can do it for you. This and this, 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 this and this. 2 times 3 gives you 6 combinations, and you just list all of the 6 combinations. Now, big word of care, especially on exam day, if there is 1,000 values in that table and 1,000 values in there, and you compute the Cartesian product, you're going to end up with 1 million values in the Cartesian product. Okay, 1 million is still fine. Let's do it again. Imagine there is 1 billion values in there and 1 billion values in there. You're going to end up, if I'm correct, with a quintillion values in there. That's going to crash the whole thing. Be very careful with the Cartesian product. This is something to be used with a lot of caution. And in fact, people rarely do the Cartesian product. They actually compute what's called a join. So what is a join? It means they don't compute all the combinations. They only take those that match. For example, there is a B colon here and a B colon here, and they only match 1 with 1 and 2 with 2, right? So it's just like the Cartesian product, but you only keep what is actually matching. This is better and efficient, and this you can do. In fact, we will do it. We do it all the time with a relational database. Okay, so far so good. Selection, projection, grouping, sorting, Cartesian product, joining, you have an intuition of that? Who is following? Who is not following? Okay, I hope most of you. And you can ask questions offline if you're completely lost. That's absolutely not a problem. All right. So let's check the time. Make sure that, oh, it's actually 10. So I'm going to leave it here. Next week, I will show you a little bit of SQL, and then we'll proceed with the exercises on SQL. There is no exercise session, but please download the Docker, try it out. If you have a problem, come on Friday. Oh. Thank you very much. I hope you enjoyed it. See you next week at 8, same room. Goodbye.